So today is linear regression, right? We want to create an equation that explains relationship between input variables and output variables. Such an equation would allow you to predict values based on certain set of parameters, certain set of variables, and it will allow you to do different type of things. Like you can use this technique to make estimation of demand. You can use this technique to predict the customer values when customers have only been using the service for a short period of time. You may use this technique in scientific experiment to extrapolate from certain set of data to the data that are outside of the scope, right? And that is the technique of regression. You can think of regression, the term itself, to refer to the reduction of forms, that you are trying to reduce the form of data from multiple points onto just an equation that explains the phenomenon. Okay, and let's take a look at the technique of simple linear regressions and multiple linear regressions on how can you do that in R. You may have already encountered, might not have been that yet. You will encounter this technique in statistics course that you will learn in the topic of trend analysis and regression itself. Okay, so topics that will be covered today are first, linear correlation. You need to be able to identify the correlation between variables, which variable would associate with which variables, and selecting those that are related to one another would allow you to create equation of relationships and use that equation to perform prediction. Then we will cover the topics of the topic of linear regression, on what is linear regression and how would that help you in predicting values. By values, I mean the numerical values, right? If you want to predict the class, then it will be the next technique, the next lecture that we will cover after the Songkran holidays. That is the classification, like classification technique. And we will start with a simple classification technique known as logistic regressions. And the third topic is building model. Right? We will look at how you can train the model. You see that there are patterns in machine learning that when you learn the concept of machine learning, you would learn the form of the model, how that model estimate its parameters or the meaning of parameters, and how the model estimate parameter from data, and how can you use the model to predict the output, and how to evaluate those models. Usually it will be in these forms on no matter what technique that you want to study and you want to use in technical sense, right? So we will learn about how to train the model in model building, how to train the model in mathematical sense and in implementational sense. And the last topic is how can you make prediction based on the model that you have, and how can you evaluate the models, what types of measurements that should be used with regression model. And these will be the topics that will be covered today. The first model that we will look at today is the model called simple linear regression. Simple linear regression is called itself as simple because it uses only one variable to explain the relationship between input and output variable. Simply speaking, you have just one output and one input variables. And this technique allows you to summarize relationship between two quantitative values. One variable would be x. X is denoted as the input, the predictor, explanatory variables, independent variables, depending on the subjects that you study. In your statistic course, you may have seen this as independent variable. In signal processing course, you may have seen this as predictors or author names. And you will want to associate x with another variables, that is y, right? Y is an output variable. This may be known as response or outcome or dependent variables. Now, what you want to do here is to associate relationship between variables. Those relationships can be deterministic in nature. Deterministic behavior, deterministic relationship has no variations, has no randomness in the data. Usually this will be from the direct calculation or from a certain equation that can be converted from one to another. Another types of relationship is known as statistical relationships. That is, you have relationship between two variables. One relate with another variable, but there are certain randomness associating with such variations. Right? How can that be? How can that be? There be variations in the data. That is because in nature there are certain randomness, especially if you are considering decision. If you are considering a lot of variables in real world that might associate with the phenomenon that you are studying. Okay, so what types of relationships are statistical relationships? Just think about the height and the weight. If I were to measure the height and the weight of everyone in this Zoom room, then I would get a bunch of data that if you plot them as a scatter plot, they would kind of scatter. And there might be a certain relationship between them. That is, usually the higher you got, the more weight that you have. But there would be certain variations and outliers as well. Or in terms of consumptions of alcohol, the amount of alcohol you consume and the amount of alcohol remaining on the blood depends on lots of factors, right? Like the metabolism of your body, like whether you have a certain disorder or not, and that would make the amount here differ from one to another. Right? That's why for some person consume a certain amount of alcohol, if you blow the detector, it might not be detected. But for some, it might be detected even if you just consume just a little amount of them. But it might remain on your system. Think about if you were bank and then you are measuring the types of data that the customers might use the card for, the credit card for. You might plot the graph between the spending amount, the amount of money spending on each time, and the number of spending of each customer, or the spending amount can be the average spending amount of that customer or the total spending amount. Plotting them both will allow you to see behavior in terms of the frequency of spending and the monetary part, right? The total amount of spending. And you might see a certain relationship between them that is like the higher number you spend, there might be like more values here, but it doesn't guarantee that, because this relationship can be in the sense that if your ticket size, the size of spending that you usually use is large but you rarely spend, then you might have low value here and high value here. So plotting relationship between them allow you to identify relationships between the two variables. You can plot the graph between the number of exercise that you have per week and the weight that you lose, right? And you might see some interesting number that, well, it might relate or not relate to one another. Okay. Lastly, you can plot the relationship between the amount of credit, like in credit card that you got, and the usage of that, and that will allow you to as well to identify a relationship between variables. You can see that in order to identify relationship between variables, the thing that you have to do is to plot the relationships, plot the graph, the scatter plot between the two variables in this case. And then once you see the patterns, you can use that to make prediction. So here we will see the two ways that will allow you to assess relationship between two variables. The first technique is scatter plot. The second, you can use correlation to identify relationships between variables. What is correlation? Correlation is the measurements of the strength and the direction of linear relationship, right? I would like to emphasize on linear here. You want to identify whether the variables have certain linear relationship with another variable or not. In terms of linear here, it means that if you change value of one variables in, say, increase the value, the other variable would probably have, if they are linearly correlated with another, they would change in the same direction or in the opposite direction, depending on whether they are positively correlated or negatively correlated. Right? Correlation is used to assess whether the two goes together. Basically, it's just that, right? And we usually use the symbol R to denote sample correlation, and symbol rho here to denote the population correlation. Right? The statistical inspiration and derivation of this would be covered, I suppose, in statistics, the course that you are learning right now as well. Right. The types of correlation that we will focus in this course, this is only one of them. There are actually plenty, a number of technique, correlation measurement technique. Like this is the correlation that the Pearson correlation is used to assess correlations in linear relationships. So how does it work? Suppose you have n pairs of observations between n pairs here may come from different, this may be x1 to xn as one data set, y1 to yn is, can be denoted as another data set. And you want to find associations between the two. So how do we say that the data are positively correlated? If the data has positive correlations, then the in terms of pairing, large X would pair with large Y. What does that mean? If you were to plotted the scatter plot between X and Y, large X and large Y would denote this point. You have a large X and large Y value, and the small x would pair with small y. That means small x pairing with small y values, and that means you would have the data that run along this axis. That is, it would kind of increasing in positive sense. On the other hand, in the negative correlation, the large x would pair with small y. That means you have a large x value pairing with a small y value, and a small x values would pairing with large y value, and it's here. And this relationship would kind of scattering along this axis. That means you would have the values look like this. So from the two, you can see that one have positive slope, another has negative slope, and that is actually the implication of positive and negative relationship. Now let's look at how can we assess the positiveness and negativeness, the sign, the polarities of these relationships, and also the magnitude of these relationships. Considering this, this is the covariance, the variation of x pairing together with the variation of y. If your data has positive relationship, well, let me put it this way. You have relationship in the positive way, and x and y, right? So if you have positive relationships, that means large x with large y, and small x would pair with small y. So I would write it like this: large x pair with large y, small x pair with small y. And once you have that, that means the x minus x bar and y minus y bar, y bar, oops, I should separate them first. y minus y bar, and the multiplication between them, x minus x bar, y minus y bar, would have certain sign, right? Like this x minus x bar, because when you have a large value of x, that would imply that the value is more than usual, more than the mean, right? That means the minus sign here, the subtraction here, will result in the positive sign. And y, if y is large as well, then it would be more than y bar, and the subtraction there would result in positive sign as well. Multiplication between the two terms results in positive sign. Okay, for small x with small y, this subtraction results in minus and minus, because x and y, if they are small, then they would be less than their own means. And the multiplication between them results in positive sign. When you sum them all, then you would get the positive, overall positive values of the signage here, right? Why, on the other hand, if you have negative relationship, you have large x paired with small x paired with large y. Let me draw a separation boundary here. Then large x would have positive amount in x minus x bar, small y have negative values, multiplication results in negative value, right? And the same go for this one as well. And when you sum the values of all terms, you would have the total value toward the minus sign. Right. So that means the SXY value here would allow you to assess the magnitude and the direction of the relationship, right? If it has positive relationship, it would have positive value. If it has negative relationship, the two data has negative relationship, then you would have the value become negative. And also the magnitude would suggest that whether it has a large positive relationship or a large negative relationship. If there are no relationship between them, what would happen? Then some would be large, some would be positive, some would be negative. When you sum all the data together, let's think about it this way. If considering that there are no relationship between them, and then you assess the value comparing to the mean of each, then you see that they would round themselves out, because some would be positive, some would be negative. When you combine them, then there will be approximately 0, and that would indicate no relationship between the two variables. Right. So that is the key to assess direction and magnitude of relationship using Pearson correlation. However, because the magnitude here is an absolute value, like you do not know whether it is very correlated or not. So in order to make them normalize into y minus 1 and 1, you can then divide the SXY with the magnitude of x and the magnitude of y. This is absolute of the sum square deviation of x and y. And you can see that this is the difference from the mean of x, assessing as the size and this square, and you have the square root here. And this is the deviation in terms of y. So you would have the size of variation in terms of x and in terms of y divided above. And it will kind of deduct from the total scale. And that will result in the values of r ranging from -1 to have to values of 1. These terms, you can rearrange them by multiplying the terms together and rearrange a bit, and then you would have the more convenient form down there. This is more convenient because from this you can assess correlations between two variables. Let me show you how it works. Right? How do I probably need to, yeah, never mind, I can do that myself later on. Okay, now let me show you how this works. First, I will write the equation of correlation. This is R equal n sigma xi yi minus sigma xi sigma yi. Sorry, yi. And then square root of n sigma xi square minus sigma xi square, and square root of n sigma yi square and minus sigma yi square. This form is actually more convenient, especially if you want to implement correlations in, say, Java, in C, that you do not want to import, or even Python, and you do not want to import the library in, because importing library means that your program would be more your program would be larger, and you need your program would depends on another library that has to be imported, and you need to install those into the system beforehand. If you just want to access correlations, this will be a good way. You can write a simple function to do this. Why is it simple? Let me show you here. Suppose you have a two array of value x and y. Say I would put the value in these terms. You have x and y, and say 0, 1, 2, 3, 4, 5 like this, and then I will just make them negatively correlated. Then that would be interesting, right? 5, 4, 3. Never mind. 2, 1, 3, 0. Yeah, something like that. And I'm going to now using this equation to compute the correlation. This can be done easily because you can see that from the equation there are elements that you can just pre-calculate it. For example, you can do the summation of xi and summation of yi. Summation of xi would be 15. Summation of yi would be 15. I did not plan this beforehand, so this is like on the fly things. Yeah, so if I made any mistake, please raise your hand or whatever, help me here as well. Okay, then and then from the equation you can see that there are the power of 2, right? So this is the x square and y square and x multiplied by y. Then the x square would be 0, 1, 4, 9, 16, 25. This is 25, 16, 4, 1, 9, and 0. And x then I need to sum them, right? And this would be 20, 30, 55, and 55. X multiplied by y. 0, 4, 4, 3, 12, 0. And the summation of x multiplied by y is 23. That is, right? Then I can plug this into the equations. And n here, n would equal 6. Then it would be 6 multiplied by 23, summation of x and y, minus summation of x, 15, summation of y, 15, divided by square root of n, 6, summation of x square, 55, and then minus summation of x, 15 square, square root of 6 and 55 minus 15 square, right? And then I need calculator. Maybe I will use R to help me here. 6 multiplied by 23, 46. So no, 6 multiplied by 23, 138 minus 15 times 15, 225 divided by square root of 6 multiplied by 55, 30, 330, and 225 square root 330 and 225, 138 minus 225 is minus 87, and then divided by 330 minus 225 minus 105, and 87 divided by 105 is minus 0.83. Right, now you can see that with the formula that I just showed you, it is quite easy to calculate the correlation. I can even do it by hand here, right? Because you need to do just the summation of that, of the 2 columns data, the 5 columns data that I have there. Okay, and this can be done by calculators, by a program that does not have libraries to support the computation of assessing relationships here. Right, let's move on. So this is how you can use the formula to do the job. Next, we are going to see and what are the meanings of correlation values. The meanings of correlation values would indicate the direction, right, and the strength of linear relationships. It doesn't indicate that they are. It doesn't indicate the slope, right? The slope of the relationship is like whether this line would be steep or whether it would be shallow. It does not imply that. What it implies is the certainty of the change, whether the change into either positive or negative signs are certain. How much certains are there? Just look at this one. This is a figure showing correlation between x and y when it has the value of 1. If you look at this for each data point here, when x value increased from this point to this point, y value always increase, right? But when there are certain uncertainty, say in this case in r equal 0.9, you can see a certain variations in the data. Sorry. And when r equal 0.5, there are more variations. When there are more variations, what happens? What happens to the certainty of change? Just look at this. Suppose you look at this point. Compare to another point when you increase the value of x. Okay, if you compare this point to this point, you can see that increasing x would increase y, right? But if you compare this point to another point here, you can see that increase x, or even this point, increase x doesn't increase y. So it's not always the case that low x pair with low y and large x pair with large y in the case that r equal low values here, r equal some not high values here. So the range of values of correlations would range from -1 to 1, with -1 indicate positive relationship, strong positive relationship, and -1 indicates strong negative relationships. And the value about 0 indicate no relationship between them. Now you see that these are the indicators of positive and negative relationships. That means when you change one value, you can use that value to predict or to estimate another value. What would be like when there are no relationships? It can be like this, that when you change x value, y does not change. That means the two are not related. Or it can be in the sense that there are no patterns at all between them, right? And then you would have no relationships between the two variables as well. All the other cases that I will show you in the next slide. How come it doesn't go away? Let me clear the annotation first. I don't know what happened. It doesn't clear out. Let me try to switch. Yeah, it's gone. Okay, so how high can you how high the correlation value should be used as a threshold to determine whether the values are strong or medium or weak. Right? Well, how do you know that the values are high enough to be called strong correlation, or whether these are the weak correlation? There are no fixed rule for that. I have this simple rule that if the values are about 1 or minus 1, right, like 0.8 to 1, then you got strong correlations. If they are like about 0, say minus 0.3 or minus 0.4 to 0.4, then you got weak relationships. Some other thing, other value like 0.6, 0.5, 0.65, 0.7 can be thought of as having moderate or medium correlations between, but there are no fixed rule here. It depends on the data, it depends on the studies. I have the work in that's in 2014, I think. My research in 2014, I used the correlation on the threshold about 0.3 to determine the weak, and 0.7 here to determine that it is strong. So it depends on the data. Some data might have like strong relationships between one another, some may not, and you need to look at the distribution to determine whether you want to call that strong correlation or not. But as I said, if the data are about 1, then those are strong values. If they are about 0, then those are the weak values. So let's look at the values, correlation values, and the shapes of scatter plot. If you have the scatter plot in this shape as a line, and you will be guaranteed to have the values of high correlation either on the positive side or on the negative side. But there is a case of the horizontal and perfectly horizontal and perfectly vertical lines. This can happen, for example, if you have the data from sensor that one sensor doesn't change at all, then correlations between that sensors and others would be 0 because it doesn't change. You cannot measure the correlation of change. Correlation measure the change of one variable to another variables. If your variables doesn't change, then it cannot be used to measure correlation, right? And also, if you can see that by having more variations, the correlation would be reduced on both positive and negative side. Okay, do not view 4 and minus 4 as one having values more than another. They are equal in magnitude, but the signs are different. The sign here indicate only polarity, whether they are positively correlated or negatively correlated, while the value indicates the magnitude of correlations. Okay, because Pearson correlation focus on assessing the linear relationships between variables. If the relationships between variables are not linear, well, these are quite interesting patterns like sinusoidal, like something like a donut here, or multi-clusters here, but they are not linearly correlated. The correlations value will be low in this case, and you need to identify this case in scatter plot to be able to know that it has certain patterns. Okay, there might be associations, but if those associations are not linear, correlation would not show. Right? That means looking at the scatter plot is important. Looking at the data visually is important. That's why a software like Power BI, Tableau, and other visualization software is the key that allow you to assess relationships in data easily. And R as well, right? R is a free software that you can create a model, you can plot graph. You can do lots of things with it. Now let's look at the code to see how you can assess relationships between the variables using correlation. You can use here. I'm going to use the empty cars data. The empty cars data. Empty car data is the data of the car specification that you can use in the demonstration here. It contains 32 observations and 11 variables. If you look at the structure here, each line indicates one. Each line is the unit of analysis. Any of you has the word research? This is not research methodology course. This is data model course. Unit of analysis doesn't imply the unit of research. Okay, right? I have not even mentioned word or terms about research at all. So if you copy the text that contains those, that's not acceptable though. So unit of analysis in this course refers to the unit that you want to study, and it associates with one row in your data table. Okay, so now we have the car model as the unit of analysis, and you would have various variables that explain the unit of analysis, like the mileage per gallon. If you want to know the meaning behind each variable, you can type the question mark and empty cars. It will show on here. It's model train car road test, right? And there are meanings of each of the variable, like a quarter mile second, weight in 100, in 1,000 pound, and rear axle ratio, horsepower, and so on. And here is the mileage per gallon, MPG, which need to be assessed using the test. So if you were able to predict this value from specification, that would be nice, right? And we are going to look at that. Okay. Now we will first determine the correlation or association between variables here. So what we can do is use correlation and empty cars. Correlation and empty cars will give you this matrix. This is the matrix of association between one variable and another variable. You can see that MPG and MPG perfectly correlate with one another. That's for sure, right? Its own value. And MPG is negatively correlated with horsepower. So the more horsepower that the car has, the less values of MPG, of the mileage per gallon. In mileage per gallon, the high is like kilolit in Thai unit. In car in Thai, that it denote the amount of fuel is will consume when you it indicate the amount of distance that the car can cover when it consumes certain unit of values there. Okay, yeah, I'm back. Right. How come it's zoom in? Is it me or no? Yeah. Okay, so using correlation allow you to assess the directions and magnitude of relationships between variables. Okay, you can also plot a scatter plot between two variables. I'm not going to plot this because I will just explain it here. If you plot the data here, and using the weight and MPG, as you can see that they are negatively correlated from the assessment using core function. You can see the trend, the downward trend here, and it looks like they are quite correlated to one another. However, you can see that there are these 3 points that are quite kind of separate from one another. And as a matter of fact, these 3 points deteriorate the values of correlations, because you can think of them as outliers, and outliers would kind of would affect the assessment of correlations here. Okay, this is negative relationships having the slope looking downward. And these are positive relationships. Again, you can see that this point extreme right point here, the rightmost point here, would deteriorate the line, because if you were to draw a line, the line would need to accommodate all the point, and it would go to something like this instead of going this way, which looks better, right? This is because the effects of outliers. So correlation is also affected with outlier. That means when you create a model using linear regression, the model itself is also affected by outliers. That means you should clean the data or treat the data to remove the outliers out, or adjust the value before putting them into linear regression model or using correlation to assess. And you can see you can see outlier and abnormalities from distributions. Distributions can use to show the trends, the location centrality, the coverness to the spread of the data, how many groups are there, and the outliers. Like this is the answer of the exam there. So here, positively correlated looks like an upward line here. And no correlations would be like this. This is between QSEC and DRAT. There are no correlation between them, almost none, about 0.1. And you can see that they are kind of scatter, right? And no patterns, no obvious pattern can be seen. And from these, you can use them to assess which variable should go with which, right? Which variable can be used to predict the variable that you want. We are interested in summarizing the trends between the two variables. That means we are looking for lines between them. Right? Scatter plot will show you the distribution and the trends. And we want to find the baseline. The baseline comes from the base parameters of the line equation, this b0 plus b1x. Or in other words, the equation that you learned that would be y equal mx plus b. Y denote the observed response or the output. X denote the predictors, the value that act as input, and y hat here denote the predicted response. We want to create an equation of predicted response which would equals the b0 plus b1 xi, right? b1 and xi. So there are two parameters here, b0 and b1. Right, the meanings of b0 and b1 would be b1 would tells you the size of change when you change x by 1, right? This is y equal mx plus b. This is like m. So it indicates if you change x by 1 unit, what would be the value of y. And b0 would tells you the intercept, right? If x equals 0, what would be the value of y? You learned this a long time ago, and actually even right now, that this is about the linear equation, the line equation. So let's now replace b0 with alpha and b1 with beta here. Then what would you have, right? From the equation, if you have a value of x1 here, plugging it into the predicted equation, the line equation, is like you project the point up to the line, and then you would get the value equal alpha plus beta x1 in this case. And this is the line that you got. Now, if you look at this green bar indicates the remaining residual. The remaining values are errors between the actual data and the predicted value. And you can see that the green bar here would be scattered about the line. So in the perfect sense, if line pass to the middle of the cloud of data, then you would have the residual distribute in normal distribution. It would be distributed in the normal distribution sense because it would kind of scatter about the line. Okay, with zero mean. So now so then it would be our task to determine how can we select the line that pass through the middle of data points. Which one is better than which one? Whether the dashed line here or the solid line here, which one is better than which one? How do we know which is better than which? We want to determine the intercept value and the slope value that are suitable for being the lines that passing through the cloud of data. Which one is the best one? Should it be the one that pass through as many points as possible? Should it be the one that pass through the middle that have minimum residual? Or should it be the one that kind of equally distributed the error on positive and negative side equally? Okay, which should be the best? And by thinking about the baseline, this would lead to the formation of optimization, right? The formation of the objective function that you can use in optimizing the baselines from the equation, finding values, finding parameters of the model, right? Which one is the best? The middle one. The middle one. You want to minimize error. You want to minimize the value of epsilon here as much as possible. How would you do that? In order to do that, you need to first define error terms. The error terms here, E or the epsilon, equals the difference between yi and yi hat, right? The predicted value and the actual value, right? You want to find the baseline that minimizes the value of error here. And because you have n data points, you would have n predictors to compare with. So you would want the values to be as small as possible in overall sense. So it means that from the errors, you want to minimize the summation of them, right? Summation of error. Oh, sorry. I think I forgot square here. Is the error square to disregard the sign, whether it's above the line or below the line, right? You want to kind of assessing only the size. And why not using absolute? If you use absolute, then you cannot use calculus. It will be difficult to use calculus, to put it this way. So use square here is better because you can use calculus, you can use derivative to solve this, right? How to solve this? We use the method called the least square method. The least square method would, well, I will ask you then, if you have a function, this function, and you expand it into yi minus b0 minus b1 xi square. A function that when you change b0 and b1, the value of error would change. Xi and yi, these are data. If you have a function and you want to find the lowest point of the function, what would you do? Think back in your 3 semester, in the past 3 semester, and the past 4 semesters. If you have, or even in your high school, if you have a function and you want to find the lowest point of the function, how can you achieve that, right? Please tell me, type in the chat. How to find the lowest point of a function. Right, you need to take the derivative, right? Differentiate, take the derivative of the functions, and then after taking derivative, and then what? Equating the derivative to 0 and solve the equations, right? And then you get the value that make this function to be the tangent, and in this case it's the 0 value at the lowest point. The tangent equals 0, right? So yeah, that's what we are going to do here. We will take derivative of the function and and then set it to 0. All right. Let me switch to whiteboard. Next page. How to go to next page? Next page. No, I need to click here. Next page. Okay. Right. We have S equal summation of I equal 1 to n. Well, in the latter terms, I will drop I equal 1 to n because we know that they will be here. I'm lazy to write them down. Right. If I'm not lazy, I will try to do that. And yi minus b0 minus b1 xi and square. Right. And you want to determine the value. The thing that we want is that we want to determine the value of b0 and b1. What should be the value of b0 and b1? So we are going to take a partial derivative because there are two values here. Curl s by curl b0. This equals 2 and then summation. Actually, it's minus 2. Summation of I equal 1 to n of yi minus b0 minus b1 xi. How do I get this one? How do I get this? I get this equation from pulling 2 down here, and then you get the same terms. And then take derivative of the inside. Derivative of the inside, when you look at this, you will see that there is only one b0, which is this one. The rest can be treated as constant. Take derivative of them results in 0 value. And because you have minus b0, that's why you got minus value here. b0 will become 1, right? And then equate it to 0. This is the first equation. Should I do that? Yeah, maybe later on. Let's make it easier first. Let's set it to 0. First equation. And then curl s by curl b1. This would be, and you can see in the equation, because b1 is attached with xi. So for this one, I would have minus 2 sigma of I equal 1 to n of yi minus b0 minus b1 xi, and time xi is equal 0. This is the second equation. Right, pulling the 2 down here, and derivative of the inside. Don't forget, you need to have the power of 1 here as well. And take derivative of the inside, you got xi, right? Minus xi as a result. So here's xi, here's minus. And then I'm going to arrange the form a bit. So here I will multiply the disregard the minus 2 on both sides and multiply from 1. I'm going to multiply it in. You got the summation of I equal 1 to n of yi, and minus summation of I equal 1 to n of b0 minus summation of I equal 1 to n of b1 xi equals 0. Rearrange the forms here. You get I'm going to move this, switch side basically. So the sum of constant value n time results in n and b0, right? And plus b1 summation of I equal 1 to n xi equals summation of yi, I from 1 to n. This is the third equation. And then from from 2. Let's rearrange this as well. Multiply it in. I have summation of I equal 1 to n of yi. And multiply x as well, right? Sorry, got to multiply x here as well, because it has xi here, so it have to be multiplied inward here, xi yi, and minus summation of b0 xi I equal 1 to n, and minus summation of b1 xi square I equal 1 to n equals 0. And rearrange the terms the same way as the above. I would have this as summation of xi I equal 1 to n, then multiply by b0, and plus summation of I equal 1 to n of xi square. This multiplied with b1, and equal summation of I equal 1 to n xi yi. This is the fourth equation. And from the third and the fourth equation, you can see it here that there are two unknowns, b0 and b1. Oops, I should b0 and b1. b0 and b1, right? Two equations, two unknown. Then you can solve this using the method to solve systems of equations. For me, I'm going to just demonstrate how to calculate the how to get the form of whatever. I'm going to do it here. So for b0, I will use the Kramer rules. Hopefully you remember that from all the classes. Sigma of yi, sigma of xi yi, and sigma of xi, sigma of xi square divided by n sigma xi, sigma xi, sigma xi square. This equals, multiply the above, you get the sigma of yi, sigma of xi square, minus sigma of xi, sigma of xi yi, divided by n sigma xi square minus sigma xi square. This is an equation for b0 to estimate the values of b0. For b1, using Kramer rule again, n sigma xi and sigma yi, sigma xi yi here divided by the same terms. So this is easy then, sigma xi, sigma xi square. Then it's easy because I can just use the above, sigma xi square minus sigma xi and square, and use the determinant, n sigma xi yi minus sigma xi sigma yi. Right. So now we have both here and here as the results, the resulting formula here and here, that you can use to estimate the value of b0 and b1. You can see that least square provide you the closed form equations that you can estimate the parameters of regression model. And actually software like Excel use these types of estimation to estimate the trend lines in the data that it has, right? So let's move on. Right. Once you are able to calculate B0 and B1, then you get the baseline out. Comparing now, if the question is which line is better one, you can compare the errors. Errors between the two lines can be done by subtracting the value between yi and y hat, and then square the values and sum them all. And then you can see that the solid line has a better errors than the dash line. That means solid line is better. Okay, and yeah, I actually forgot to cover this before. So in order to find the best point is to use method of least square, finding the location that you got the lowest error, the error as lowest point here. And I have already shown you how to do that. Now, once you get parameters, you need to assess the fitness, right? The fitness of the model parameters and the data. How can you do that? Right? One way is to do the same thing as this. That is, you can calculate the sum of square error. Right? This value is called the sum of square error, because you got square error and then you sum them. That's why it's called sum of the square error. It tells you the error that it has. The lower, the better. Nah, it doesn't clear out. Let me switch. Yeah, this help. All right. But there is a better way to assess that in terms of the predictability of the model. That is the use of coefficient of determination, or the R square. R square indicates the proportion of variance that the model can predict. To illustrate that, let's look at this figure. This figure, you have the data points in the X mark here, and these data point has the mean values at the green line. From the green line, if you draw the difference between the data point and the line, you get the total variations of the data. Now, in the regression model, we are trying to predict a line, right? The solid line here, the black solid line here, and this black solid line, when you make prediction at certain x, when you make prediction at this point, it would kind of raise the values of y of the prediction from the mean to this value. That make you have this red part. The red part here is the variations that the model explain, and that it gain comparing to using just the mean. And you also have the black part here. The black part here is the unexplained variation that the model has not explained. In other words, the black part here is the error that we have talked about earlier, right? So what does that mean? It means that if you were to compare the blue part with the red part, you would get the you compare the blue part with the black part, you would get the red part. And our idea is to assess the proportion of the red part here, the explained variation, with the total variations. If your model can explain variations in data, the higher values it has, the better it gets, right? So in order to assess that, you can use the calculation of R squared to determine that the model can explain variations or the variance in data or not. How to do so? We can do it so by, like I said, using the blue part and the black part. This is the blue part, SSYY. This is the sum square of y, right? The sum square of y is drawn from the comparison from the point to the mean, right? This is SSYY. If you take SSYY and minus SSE, right? SSE is this part. Well, if I were to put it this way, this is the SSYY calculation, and this is the SSE calculation, the sum square error calculation. By subtracting them, SSYY minus SSE, you get the explained variance. You get the explained variations. And then divide them by SSYY. And the value here would be ranging from 0 to 1 approximately, or minus value, some minus value if you get like totally wrong line to 1. Okay, so here SSYY divided by SSYY equal 1 and minus SSE divided by SSYY. You get the latter terms. This measures the relative size between the errors and the explained variance and YY. Right? The smaller the SSE, the better the predictions. How do you obtain SSYY and SSE? SSYY is the subtraction, the difference between the actual value and the mean. So this would indicate variations in data. While SSE indicate the difference between the model, YI here, and the actual data, right? And sum them all here, and then you get a general sense on how your model can predict the data. The value of high square, the better the model, the higher the values. You want the value to be high. The value itself would take, sorry, I need to fix this. It actually doesn't take the value between 0 and 1. 1 here is maximum, but it would be, the value here can be also in the negative range as well if the model is entirely wrong, right? But it would be weird because you are using least square to fit the model. That means it obtain the baseline for you, right? But if your model is wrong, it means that there must be something wrong, right? The data might contain lots of outliers. To be able to use with linear regression, you need to clean the data first. So if you ever spot negative R square, you probably need to check out your data. There might be something wrong with the distribution of data or other things. Okay. But the maximum value is 1. You want the value to be as high as possible. Okay, so R square indicate the how your model fit with the data. It also indicate how how much X contains data about Y. Okay, right. So comparing to using just mean. Let's look at how you can create the regression model. This equation I use weight to predict MPG. So from this one, you can use the function LM. LM has this. Let's look at the help first. Oh, I forgot to switch the screen. Here, this is the help of LM with fitting linear model, and you need to provide with formula and the data. Yeah, I'm going to use LM model here to be LM, and this would be MPG tilde WT, right? And using the empty cars data. And from the model, you can use summary to get the summary of the model out. And here is the summary of the model. It will tell you the residual distribution. So you can associate whether the model fit the data well. If the mean or the median's value about 0, then it means that it's okay. It's passed through the middle of the line. If not, then that means there's certain deviation. There might be some outliers in the data. And it also tells you the coefficients value, the estimation of coefficient, and the intercept and the weight, the slope, right, of the lines. And as you may have learned in your statistic course, you can make hypothesis testing of the data, right? These are the standard errors from the model, and it used the t-test to compare the value of the parameters with 0, right? Comparing value of parameters with 0 and determine the p-value, which would indicate whether this is significantly different from 0 or not, Right. At your level here, I would expect just that you know that these are the parameters. Right? The estimate value here are the parameters, and if they are not, if they are like have values that are not zero, right? That are obviously not zero. Then it means that you should include this parameter in the model. And down here, it provides you with the residual standard errors, which give you the assessment of the variations in terms of data. And it also tells you the R-square value in terms of the R-square in the raw sense, the multiple R-square, and the adjusted R-square, which dump it down a bit by adjusting it with the number of parameters. So you can take a look at the adjusted R-square later on if you are interested in linear regression. It's just certain correction equation that adjust the number of parameters from n to n-1, obviously, that because you have a higher value of the variables that you have here. Right. So by running the LM here, you are creating a model that fit with the data already, that you have the slope equal -5 and the intercept equal 37. Let's look at the explanation here. The estimate in the coefficient indicate the value of coefficients. Standard errors. This is the measurement of the variation. It measures the average amount that the coefficient would vary from the average value of the response variable. Basically, it tells you if you change, it tells you the variations of data in terms of with respect to these coefficients, and t here indicate the t value in t-test that you use both estimate and standard error. Then you can calculate the comparisons between the estimate and zero and the variations, and use both to assess the probability whether estimate is significantly different from zero or not. And down in the bottom side here, you get the values of R-square and residual. Residual values indicate the average amount of response that are deviated. They are deviating from the true line. So basically, it tells you the average errors of the data, of the prediction from the data. And and R-square indicate the fitness, right? In multiple regression that you will see later on, R-square will be increased when you put in more variables. So there is a value of adjusted R-square which should be used if you use multiple variables, not simple regression, but in terms of multiple regressions. The last one, F statistics. F statistics is usually used to compare the proportion between this. This is in. Have you learned that this in statistics course yet? The F statistics. The T and the F. Have you learned that t-test and f-test yet in your course? Yes, right? Okay. F statistics is used to compare proportions, two proportions with another, right? Usually it's used to compare the variations between groups and variation within groups. This is used to compare the whether the model, let me take it a bit here. Right, sorry, there are lots of distractions at home here. Right, F statistics is used to tell us whether the deviation that we see from the model, comparing to the variations using variance, whether it reduces whether one is better than another or not, by comparing the variation from the data to the variations when you use the model. The variation when you use the model should be lower, and comparing them, you see the improvement. So if it's further from 1, then it's better, right? So that means when you look at the f stat in the equation here, in the value here, the more value it has, the better, because it would indicate that the model is contains certain information about the prediction. And p-value is the p-values of this f statistics. Right. To use the model for prediction, you can just use the model with the function predict and the data that you have here. At this point, I have not separated the data into train set and test set yet. So what we are using here is to use the old data that you train the model to predict itself, which will get lots of fitness here, but it can be overfitted. Okay, use empty car with the model and function predict allow you to predict the value out. This is like you are interpolating or estimating the values based on the parameters that you use. And parameters that you used here contains the only WT, right? Using weight to predict the values, the output. Comparing to this one, HP and displacement. In HP and displacement, you can see that R square is a lot lower. Here you are predicting HP from the size of the car, which shouldn't be related much. That's why the value is low. Okay. And again, this is for positive relationships. The reason I show you this, you can see that the estimate here is positive. In no relationship between quarter millisecond and DRAT, you can see that here is positive, but well, p-value is not significant. R square is really low. The value actually go along with one another here to indicate that the model cannot be used to predict the values. And the lastly, the topic that I will say briefly cover to show you that you can do multiple regression of multiple variables, which work the same way. Actually, you can take derivative of multiple variables like this, and then solve systems of equation that contain multiple variables. But we are not going to, let's say, do it in analytical sense, in formula sense here. We are going to use R to do the job here. So multiple regression contains more than 2 variables, more than 1 variables in predictor to create the models. The form looks like this. You have the function fx equal the w0 plus w1 x1 plus w2 x2 and so on. You have multiple variables, then you can put them there, and then there will be multiple coefficients associating with each variable. I would say there will be a coefficient associating with each variable, so there would be multiple coefficients there. Like this one, if you create a model using MPG tilde WT plus HP, it means that you want to predict MPG using both WT and HP. Oh, I don't have to use the string sign, right? And you can see that R square is boosted from has been boosted from 0.7 to 0.8 here. It means that it can explain 82% of variations, and these are the estimates equation. So if I were to write equations here, it's actually y MPG. Let's use the MPG equal 37.22 minus 3.8988 WT minus 0.03 HP. This is the equation that you got from the estimations. You can also include interaction term. Interaction terms is the terms that you cannot look at one variable, but you need to combine them, right, in order to explain that there are certain interaction between variables, between the things to get the results. For example, think about drug and alcohol. These two may act together and create adverse effect, right? Or if you look at the data from customer, the type of credit card that they use and number of times that they are active in each month might be might result in different type of spending result. So there, like on the time you spend with the book and the time you spend with writing code may result in different score in this class. For example, there might be certain interactions between them. Right? So interactions refer to the terms that the factors are not totally linearly associated with the result. Right? There might be some adverse effect, right? Vaccines adverse effect, or other thing. So there might be certain interaction between factor, and those interaction can be in positive side or negative side, right? We can include them into the model by using the star sign here, and you will get the HP and colon WT here. This denote the equation like, so if I were to write the result, and you can see that the R square is higher because you get more terms. How comes you just have the WT and HP? How comes you get higher results with interaction models? The model here actually look like this in the form of equations. You got 49.8 minus 8.2. I will just use one decimal here. WT minus 0.12 HP and plus 0.0. I need to use 2 digit. 0.0 T WT time HP. Interaction terms is the multiplication between the two. Okay, and from the sign here, this is interesting. It means that the weight and the horsepower is, these two are negatively correlated with the fuel consumptions. That means the larger the car, the heavier the car you have, the worse mileage per gallon that it will have. Right, higher value of weight results in lower value of MPG. Higher value of horsepower, the powerful car would also lower MPG as well. But if both come together, you have higher value, higher HP. Actually, it would contribute into positive side. If you have both weight and horsepower goes together, then it results in the better performance. But if one go without another, go into the opposite direction, it results in the negative performance. All right, so this is interesting because you now have interaction terms, and it actually improves the quality of the models. Okay, this is interactions. Right, and that is the end of today's lecture. Right. Today's lectures cover the topics of regressions. You will learn that in your statistics again, for sure, I think. And from here, this is like the first model in machine learning, because we are training the machine learning to the regression model to learn the line. Once it learns the line, you can use the line to make prediction of the values. The assignment today is to predict the demand. So here is the data collected from the logistic company, 60 days. It has 12 predictors. For each day, it has 12 predictors and the target that you should predict. And the target is the number of orders daily. Okay. So we want to create regression model that would predict the daily. That would predicting daily, and what it would predict would be the daily demand. It would predict the daily demand or the total number of order. Total number of order. And you see in the examples, this lab, that sometimes adding predictor will not help predictions. Right? I want you to experiment and find the best form that would give you highest R square. All right? I will post the data later today. You can download the data and then do the lab and submit it after the break, right? Next time we see each other, so you have about 2 weeks to do this lab, because next week is Songkran holiday. So have a good weekend and see you again. See you again after the breaks. Oh, before I forgot, right? I also posted the project, right? The term project for this course. In the term project, you need to select one data set that you like, a group of 5, and then select one data set and perform as stated in the sheet, the visualization, analysis, and the model that you choose. Okay. Do not copy from the internet, because I would know. That's obvious. I can use search engine, right? My work in my research before working on this is actually creating search engine. I taught the search engine course. So don't, and you use search engine to search for that and copy everything there. It's obvious. Plagiarism is 0. I mean, in terms of score. So do not copy from internet. Do not copy from Kaggle. Try do them yourself. That is the meaning of learning, right? You learn things by doing, not by copying. Copying will not give you any skill. Just think about playing games. If you are not playing games, if you are not actually put dedication into that, you will not gain skill, right? What this course is about is to encourage you to gaining skill in data that will be beneficial to you guys in the futures. So this is the end of today's lecture, and hope you enjoyed it somehow. I will post the lectures or lives in few days. I will editing this one. I will edit this one to be in the proper form, and that's it. If you have questions, post them into the Facebook group. For today, goodbye.